It may look like an ordinary star, but S301 was recently discovered to be quite the cosmic record breaker. Not only is it the fastest star ever measured, but it also comes closer than any star observed before to the supermassive black hole lurking at the center of our galaxy. As such, it holds the key to testing one of the most famous physics theories of all time, Einstein's theory of general relativity. S301 was first glimpsed in spring 2023 using gravity on ESO's Very Large Telescope Interferometer, or VLTI for short. We did a whole video about VLTI and just how powerful it is, which you can see here. After the discovery of S301, the research team led by the Max Planck Institute for Extraterrestrial Physics continued tracking it. They quickly found that this star was special. It was the closest star ever discovered to the supermassive black hole at the center of our galaxy, Sagittarius A star, and it approaches to just 12 times the Earth-Sun distance, which is next to nothing in astronomical terms. Just for reference, the closest star to the Sun is over 20,000 times further away. But how did S301 get so close to the monster at the center of our galaxy? Being an average run-of-the-mill star, consensus is that it can't have formed there, because the gravity of the black hole would have ripped apart any clouds of gas and dust from which it could have formed. Instead, it is thought that S301 was originally part of a pair, called a binary system, that got just a little too close to the black hole. While its companion was shot off into space, S301 remained in an extreme elliptical orbit around the black hole, reaching speeds of up to 25,000 kilometers per second, which is about 100,000 times faster than a commercial plane, or over 8% the speed of light. This all sounds rather unpleasant and stressful for S301, but for us astronomers, its misfortune represents a unique opportunity. By getting so close to Sagittarius A star, S301 holds the potential to probe deep within the gravitational field of a supermassive black hole and put Einstein's theory of general relativity, our best current theory of gravity, to the ultimate test. Published by Einstein in 1915, the theory of general relativity states that matter and energy shape space-time. Put in the words of physicist John Wheeler, space-time tells matter how to move. Matter tells space-time how to curve. A black hole is the most extreme distortion of space-time that we know of, and therefore it's an ideal testbed for general relativity. Quite conveniently for us astrophysicists, the curvature of space-time around a black hole should depend on only two things: its mass and its rotation rate, also known as spin. Simple, really. The problem is that black holes are by definition black. They don't emit radiation, and we can't observe them directly. So in order to get a handle on them, we need to see how they affect things around them. For instance, nearby stars. Being by far our closest supermassive black hole, Sagittarius A star is the only black hole for which we can measure the orbits of individual nearby stars directly. But close is still relative. Sag A star is a whopping 26,000 light years away from us, making the observation of any stars in its vicinity extremely challenging. In fact, we've so far only been able to detect a handful of stars in a close orbit around this black hole, the S stars. It was by tracking the orbital motions of these stars using ESO telescopes that astronomers were first able to confirm the very existence of our supermassive black hole, a discovery that was awarded the 2020 Nobel Prize for Physics. Further detailed observations of the S stars have already revealed key facts about our supermassive black hole, Sag A star, such as its mass, a whopping 4 million solar masses, and confirmed key predictions of general relativity, such as Schwarzschild precession and gravitational redshift. If we want to take the test of general relativity to the next level, the logical step is to measure the spin of Sag A star. Like most things in the universe, we predict it rotates, but it's not yet been possible to measure its spin directly, nor the spin of any other black hole for that matter. But knowing the spin of a black hole is critical for understanding a really cool feature of general relativity. Unlike Newton's classical theory of gravity, where a spinning mass will exert the same gravitational pull as a non-rotating mass, general relativity predicts something known as Lense-Thirring precession. Objects that come close enough to a rotating mass will experience the swirling curvature of space-time and take a slightly different path to the one they would have taken if the mass was not rotating. However, this effect is only noticeable very, very close to a black hole, so it's not enough to track just any S star, but we need one that's extremely close to Sag A star. And this is where S301 comes in. Following the discovery of this special star, the team have been monitoring it closely to constrain its orbit. Going back to data taken in 2017, they were able to find S301 also in these older measurements and determined that it last made its closest approach to Sag A star in early 2023. After months of detailed modelling, it became clear that indeed S301 is sensitive to the effects of a swirling space-time. And what's more, since it completes an orbit in just 8.7 years, a human-friendly timescale, we may be just a decade away from measuring the spin of Sag A star, a dream come true. The next closest approach to the black hole will occur in 2031, by which time ESO's Extremely Large Telescope, or ELT, with its immense light-gathering powers should be operational. Follow-up observations, both with the VLTI and the ELT, are crucial for measuring two complete orbits around the black hole, which is necessary for determining its spin. So far, Einstein's theory of general relativity has stood the test of time and held up to any observations us humans have thrown at it. But the question is, will it also pass this ultimate test? Stay tuned, continue watching Chasing Starlight for the next 10 or so years and find out.